This is the second portion of section 9.4. Now, on this page, this set of theorems seems a little intimidating, but these are just theorems that mirror exactly the theorems we've already seen in chapter 4. So let me just remind you, in chapter 4, we had the superposition principle for homogeneous linear differential equations, which said that if we had two solutions, then any linear combination was also a solution. And we also had a theorem that told us about when we had a general solution of a homogeneous differential equation, and the test was if we had two solutions, we had to make sure their Wronskian was not equal to 0, and then those two solutions formed a fundamental set. And one more thing, the solution structure of the non-homogeneous told us that we could get the general solution of the non-homogeneous by taking any particular solution of the non-homogeneous, which we called YP, and adding it to the general solution of the homogeneous. So back to chapter 9, these theorems say the same thing, except it's a higher dimension. So we've got a superposition principle for homogeneous. We've got the solution structure for non-homogeneous. Here's an example of superposition for the homogeneous. And we also have the Wronskian, which there's a slight change here in the Wronskian definition. So the criterion for fundamental sets is the same. You have a fundamental set if the Wronskian is not equal to 0, but the Wronskian, before, the Wronskian was the determinant y1, y2, y1 prime, y2 prime. Now the Wronskian is just the determinant of the solutions going in as column vectors. So you don't take any derivatives. You put your n solutions in as n columns, and you take the determinant of that matrix. And that matrix, without the determinant there, that matrix is called the fundamental matrix. All right, so let's just see how this works with a real life example. So we've got a matrix here, A, given that both x1 and x2 are solutions of x prime equals ax. So that's the system x. If big X is, let's say, little x, little y, then x prime equals ax is x prime y prime equals a 1, 4, 3, 2 x y. All right, so given that we have two solutions, do they form a fundamental set? If so, write down the general solution and the fundamental matrix. So again, we're given these solutions. In the next section, we'll actually be able to find these solutions. In order to put x1 and x2 in as columns to find the Wronskian, we need to write them as column vectors. So we need to distribute the e. So x1 is actually negative 4 e to the negative 2t, 3 e to the negative 2t. Because if we leave it like this, there's no way to put it into a matrix. So here we want negative 4 e to the negative 2t, 3 e to the negative 2t. That's our first column. And our second column is, again, distribute the e to the 5t, e to the 5t, e to the 5t. You're not taking any derivatives. You're just putting, go back here, you're just putting x1 and x, in this case there's only 2, and x2 in as columns of a matrix, and you're finding the determinant. So you can either use this notation, W is that, or put brackets on this and write DET out front. Either or is fine. All right, so this is negative 4 e to the, we add the exponents, 3t, minus 3e to the 3t, which is negative 7 e to the 3t, which is never 0. So yes, x1, x2 form a fundamental set. And the general solution okay, so back up to this box here. If you do have a fundamental set and the Wronskian's non-zero, then the general solution is found by multiplying each x by a constant and then adding. So take a linear combination. So in this case, big X is C1 x1 negative 4, 3 e to the negative 2t plus C2 x2 1, 1 e to the 5t. And it's fine if you want to distribute the e's like we did to find the Wronskian. So that is equal to C1 negative 4 e to the negative 2t, 3 e to the negative 2t, plus C2 e to the 5t, e to the 5t. But typically we don't do that. We do it to find the Wronskian, but when we're writing down the general solution, we'll leave the e factored out. All right, and so this question actually was asking 3 things. Do they form a fundamental set? What's the general solution? And then the fundamental matrix is, so back to our box here, the fundamental matrix is just the matrix with x1 through xn in as columns. So it's the exact same matrix that you took the determinant of to find the Wronskian. So here, there is no choice. You have to distribute those e's. So negative 4 e to the negative 2t, 3 e to the negative 2t, and then e to the 5t, e to the 5t. Okay, and then this one's super quick. Given a particular solution of a non-homogeneous system, A is in the example above, and F is this vector, write down the general solution of the non-homogeneous. So our general solution is big X equals XP plus XC. And so how am I getting that? I'm using this theorem right here that tells me the structure of the non-homogeneous general solution. Okay, and so XP is given to us as 2, negative 1, t plus 9, 1. And XC, we found in the previous problem, that's C1, negative 4, 3, e to the negative 2t, plus C2, 1, 1, e to the 5t. All right. Now here's a practice problem for you to do, very similar to the one I just did. So before we move on, I suggest you pause the video and make sure you can do that, and then check your answer because the solution's at the end. All right, one more topic before we go, and this is a preview to the next section. So you won't find homework problems like this week, but you will next week. All right, so eigenvalues and eigenvectors. If you take a non-zero vector, multiply by a matrix, and you end up with a multiple of that vector, then we call that vector an eigenvector, and we call that multiple an eigenvalue. So this is very special. In general, when you take a matrix and multiply by a vector, you're not going to get just a multiple of the vector that you started with. Okay, but if you do, then that's an eigenvalue eigenvector pair that you found. So the actual definition is, if you have an n by n matrix, R is an eigenvalue of A, if there's a non-zero vector k such that ak is rk. We use lambda, I think, in Math 3A, but in this textbook they use r, so I'm going to stick with r. And k is called an eigenvector. So here's how you find eigenvectors and eigenvalues. I'm just going to state this without proof. It takes a whole course to prove this, but a linear algebra course. To find eigenvalues, you're going to solve what we call the characteristic equation, which is the determinant of a minus ri equals 0. Now, we've already done that. An example of that is, was it this section or the last section? I believe it was at the very end of the last section, 9.1 through 9.3, we found the values of r for which the determinant of a minus ri was 0. Okay, so we'll be doing that again. All right, got to find my place here. All right, and then to find eigenvectors, which we haven't done yet, we're going to solve a minus ri times k, where k is a vector, set that equal to 0. So that's basically solving a linear system, and we have done that, just not in this context. So let's just walk through an example and do both of these things. So 1, find the eigenvalues of a. So for 1, we're going to solve determinant a minus ri equals 0. So that's 0 equals the determinant. A minus ri, we're just going to subtract r from the main diagonal. 1 minus r, 1, negative 2, 4 minus r. All right, and that's 1 minus r times 4 minus r is r squared minus, let's see, 5r plus 4. And then I'm going to subtract negative 2. So that's r squared minus 5r plus 6. All right, and that factors as r minus 2, r minus 3. So notice I have a 0 equals there. That's an equation. So the solutions to that equation are 2 and 3. Those are our eigenvalues. Step 2, for each eigenvalue, find one corresponding eigenvector without fractions. So we're going to have to do 2 separate calculations here, one for r equals 2 and one for r equals 3. For r equals 2, I want to solve a minus 2i times k equals 0. So I'm looking up in this box here, I'm solving that equation. All right, so let's write out what that is. That's a minus 2i. If you set r equal to 2 in this matrix up here, 1 minus 2 is negative 1, and then 1, and then negative 2. 4 minus 2 is 2. Big K is K1, K2. And that's equal to 0. Now, we can't have a scalar there because this is going to be a vector, and so it has to be equal to the 0 vector. So this 0 here indicates the 0 vector. There's our linear system. So let's solve that. First, I'm going to write it out as a linear system. So if you're in Math 3A, you're welcome to solve this by reducing the augmented matrix. But I'm not going to do that here. I'm just going to write out the system and solve it the old-fashioned way. This is negative k1 plus k2 equals 0, and negative 2k1 plus 2k2 is 0. The second equation is 2 times the first equation, so you can ignore it. So I'm going to solve for k1 in terms of k2, and I get k1 equals k2. So a typical solution looks like a big K equal K1, which is K2, K2, for any K2. So I'm going to take I want one vector without fractions. So I'm just going to take the simplest value of k2 I can think of. How about 1? So big K, and I'm going to call it big K1 because we're going to get another K from the second eigenvalue, and I'll have a big K2. So big K1 is 1, 1. That's an eigenvector for the eigenvalue r equals 2. All right, you might want to pause the video and make sure you can find an eigenvector for r equals 3. And then come back and I'll do it. So we're back. R equals 3. I want to solve, and I'm going to want to see this in your work. When you do your next test, I'm going to want to see all this stuff. We're going to solve a minus 3i times big K is 0. Now this is a vector and that's a vector. So let's write out what those are. A minus 3i, take a and subtract 3 off the main diagonal, and we get negative 2, sorry about that, negative 2, 1, negative 2, subtract 1, 3. So 4 minus 3 is 1. And then K1, K2 equals 0, 0. So that gives me two equations. Hang on one second. Bread's done. Okay, I'm back. This gives us two equations. Negative 2k1 plus k2 is 0, and negative 2k1 plus k2 is 0. Okay, I think we can all see that the second equation is not needed. So let's solve for k1 in terms of k2, and we get k1 is positive 1/2 k2. So I'm going to take k2 equal to 2 so I can clear fractions. And so I have my big K2 is going to be, let me just do the intermediate step. My big K is of the form K1, K2, but K1 is 1/2 K2, and K2 is just K2. But I'm taking little k2 to be 2, so I have a 2 here and a 1 there. And there is my eigenvector for r equals 3. Okay, we'll do more of this in the next section. And that's it for today.